Okay, good afternoon, everybody. I hope everyone's having a wonderful day. So before we get started, I just want to remind you that the last assignment is due by the end of Friday. The 8:30 rule is in effect, so you can submit until 8:30 in the morning on Saturday. So yeah, that is coming up very soon. For those that are graduate students, just be aware that the interviews are starting next week. Every student in 811 has registered a time slot with me. So when you come and do the interview with me, just I want to mention this up front. I do have a document obviously explaining these things on the course website, but you'll be copping on in at the time that you've assigned, that you've picked out of the time slots. Hopefully you're able to view that after the fact. If not, somebody could confirm that with me. But I've seen that every student in 811 has registered a slot, which is great. And I'm looking forward to doing these interviews with everybody. So, but yeah, that's really all the main bit of news when it comes to this. I will be putting out that exam format as soon as possible. So I was hoping by the end of today, but we'll see. There's a lot of things I have to get done by the end of today, but I am going to be pushing very hard to try to do that. Okay, I'll be trying my best, which should probably mean yes. Yes, you should expect it much later on today. So, are there any questions or concerns before we get started? So don't be shy about asking questions. Give me 2 thumbs up if we're ready to go, because I'm going to take us on quite a ride today. Okay, awesome, awesome. Okay. So last day I had defined, at the end of class, I defined the complexity class, NP, which for every K, there exists, so I consider N time, remember, this is the class of all polynomial time, these are languages for which there exists a non-deterministic Turing machine that has time complexity n to the k for some K. So, one question I have for you, and this is a good way for me to start this lecture, is asking you, because last day I also defined what P is. Can somebody tell me, is P a subset of NP? When I say this, I mean just, is it some subset of it? So I want you to think about it. So remember the definition of a deterministic Turing machine versus a non-deterministic Turing machine. So if I gave you a decision problem or a language, and I told you, oh yeah, it's in P, that means that there exists some deterministic Turing machine that has time complexity that is some polynomial. And I tell you, okay, is the same language, is that sitting in NP somewhere? That's really what I'm asking you. Yeah, it sounds like it would be true, right? And in fact, it is. So you might ask why. Now, the Turing machine-based explanation for this would be very simple. It's actually very similar to something I showed you near the beginning of this course. Now, do you remember that in that proof where I showed you how to take a DFA and turn it into an NFA? Do you remember I told you it was almost like cheating? And I told you, oh yeah, all I do is I take the transition and I put curly braces around it. Do you remember that way back? Like this was something I did like a while ago. Like this is near the beginning of the course. I used a trick very much like that. You can do the exact same thing with a deterministic Turing machine and a non-deterministic Turing machine. So all you do is you take each one of your transitions or moves. So remember you have your state and a tape symbol you read, and it has that triple, right? All you do is you put curly braces around that. And that's a single possible move that you can make. And that's true for any deterministic Turing machine, right? I just put it in the curly braces, and now you just have one move as opposed to a set. So it is indeed a set of moves, right? That it could happen. It's some choice I can make. So that's actually why you could say this, is that for any one deterministic Turing machine, I can give you a non-deterministic Turing machine, and it also runs in polynomial time. But the thing is that we're only talking about things that are in P when I say this. Not to be confused with me saying things that are in NP, because that means something very different. We're going to address that in a moment. So is that clear, everybody? I'll give you another way of thinking about this question in a moment, because I'm going to give you another way of thinking about the class NP. And this is one that I consider rather valuable if you want to prove claims about whether a problem or language is an NP. So I'm going to define something we're going to call a polynomial time verifier. Some people will call this a polynomial time verification algorithm. But I'm going to first tell you what a verifier or verification algorithm is. So a verifier for some problem or language, pi, is an algorithm A. So remember A, you think of A here as a decider, if you want to be very technical with this, where if I look at pi, remember this is the language I'm looking at, if I have W as a member of pi, it has to be that this algorithm A accepts a pair WC for some string C. Now you might ask, what is this C? That's so weird, right? Like, we haven't seen anything like this before in this course. So now C has a very special name. It's oftentimes called a certificate or proof. In some other circles, they like to call it a witness. But I want to give you kind of I want to kind of take a step back. So suppose I gave you, remember I talked about how problem instances can be thought of in a decision sense as a yes instance or a no instance or just complete garbage. They can be things that don't even make sense within the confines of the problem, right? So if I give you a yes instance, what would this do? So if I give you something that's that means that this W actually belongs to this language, pi. So what the verification or this verifier will do is this algorithm has to accept, given W and this thing we call a certificate, and I get to choose what the certificate looks like. So notice the quantifier here. It says for some as opposed to any C. So can C be the empty string? I'll get to that in a moment. That's a wonderful question. That's a very wonderful question. I will be elaborating on that in one moment. So if I give you this and I tell you, okay, so that's what a verifier does, and I get to pick what C is. So you could think of the certificate or proof. So if I give you a yes instance of a problem, what my job is to do is I'm going to try to verify using C that W is in that language. So you can look at this like if somebody came along to you and says, like, hey Dan, and they give me both this instance or input W, and it gives me this certificate C, and they're telling me, hey, look, whenever this is actually a yes, the answer is supposed to be yes, as in W is in that language. The certificate C has to provide me proof that it indeed is a yes. But they get to tell me what C is. They come over to me and they're like, hey, Dan, I got a proof showing you that this thing is in fact in that language. Now, I'm going to add an additional constraint that's going to make this more interesting. So the way you can think about this is that somebody provides you a short description to check if, in fact, and this proof is C, remember? They provide you some proof to check if W is in the language. That's really what the point of C is. So C might look like complete garbage, but the thing is, we are allowed to pick what C is. So we can actually instill meaning into C. So we're going to see that very often is we're going to prescribe that the certificate is in fact something that's related to that problem. We're going to see that with a couple of examples. So what we're going to impose on top of this is that we want to get polynomial time verifiers. So that I'm going to impose that A over here has to run in polynomial time with respect to the length of W, so the input length. So you might ask, what does that mean when I have a C right here? So look, there's W and C when I talk about this verifier, right? So notice that I'm saying it's polynomial in the length of W. I say nothing about C. So that means that when I measure the time complexity of A, it has to be that this C must actually also be of polynomial length, because otherwise I can't check it in polynomial time. So you got to imagine like I have some encoding with W and C, and the whole idea is that I want to check C, right? But I can't check C in its entirety if it's longer than some polynomial with respect to the input length. So that's a very subtle but important constraint that's placed on the proof or certificate. So does everybody see that? So you just think of C as some string, and its job is to tell, I'm going to use that to help me verify that W is in fact in the language. So I'm just going to care about what C is when I do this. We're going to see this with our examples. So when I have one of these, I can say that pi is polynomially, it's a Wednesday, a polynomially verifiable if it has a polynomial time verifier. So if you're thinking about what exactly does this mean and why do I care that these certificates aren't very long, you can think of it like I'm trying to characterize when I impose this that there are short proofs that are easy to check. So remember, the proof is C. And remember, my responsibility when I give you one of these verifiers is just that whenever there's a yes instance or W's in the language, it has to be that my certificate of polynomial length with respect to W, it has to be that it answers, of course, yes when I check it. But if I give you any other type of proof, so if I give you a no instance, so if I give you something that is not in pi, and I give it to A, it has to be that it just simply rejects on all such things. Now, this is not to be confused with something that I need to point out, and I'll point it out in a moment, because it's a very common mistake that some students make, and even some people that actually work in this kind of area sometimes get backwards. And it happens every once in a while, but it's a fundamental idea. But I want to draw you on a connection between the concept I described here and these polynomial time verifiers. Remember, I'm going to give you a couple of examples of these verifiers, so don't worry if this seems a little too abstract at the moment. Just remember that there's going to be this algorithm that takes the input and this proof that exists, and it's got to be able to accept if W is in the language. So here's the important connection. This is another way you can characterize NP, is that there's a polynomial time non-deterministic Turing machine if and only if there's a polynomial time verifier. So if you could present me a polynomial time verifier, and it obviously works, if that's the case, then there's actually a way you can translate this into a polynomial time non-deterministic Turing machine, and also vice versa. I want to give you just an intuition behind it. If you're curious more about the details, I believe Hopcroft actually has some details about this, but I find the proof in CIPSR is really easy to follow. I like it. But I'm going to just because of the constraints on time, I'm going to give you just an intuition behind this. And I think that this usually helps quite a bit when you're thinking about this. Okay, so remember, when I defined time complexity, we cared a lot about the idea that there's some point for which all my computational branches, at some point, all of these have to halt, right? So there might be some over here. And suppose I have this one right here. And it accepts for my non-deterministic Turing machine. So you might ask, Dan, what does this polynomial time verifier have to do with the computation tree that we had for our non-deterministic Turing machine? Okay, so you know that the non-deterministic Turing machine with its clairvoyant powers will know to go this way over here, right? If there's a yes instance, it will find it. If there is a no instance that's presented, i.e. the string is not in the language, that means it's just going to have to consider all possible ones of these execution paths, and it has to reject on all of them, right? If we're talking about a decider, right? Am I making sense to everybody? So that's what we do with a non-deterministic Turing machine, right? So what you can think about this as, when I give you this path that's in my computation tree, you can think of the decisions that I make along this path as those that would correspond to the certificate. So for example, if I make a guess, you're going to see this often with my examples. If I pick an appropriate certificate, what I can do is I can imagine I'm making guesses of what the answer is for my input W. So if I do that, I can make some guess. And now with the non-deterministic Turing machine, it most certainly will make the correct guess, right? I just don't know what it is. This thing knows how to do it, right? It's some magical stuff, right? So if I make this guess, I want some way to check it, right? But what's the check part of this? It's this path right here. But what's the length of this path? Well, it's going most certainly, if it's going to be related to the certificate, it has to relate to the length of the certificate. So do you see how if my certificate is only polynomial in the length of the input, I can guarantee you that this path right here is most certainly going to be some polynomial with respect to the input length. Does everybody see that? So that's the high-level way of viewing why we can kind of get away with this. Now, you might ask, Dan, well, what if you give me no? Well, remember, if I give you a certificate and I know the algorithm is given some no instance, remember, it's not responsible by that definition to say anything about rejecting, right? So it's not responsible for checking all of these paths, right? So if I give you one path along here, the responsibility of my verifier is just to say no, right? It's supposed to reject. So just going to walk back over this way just to clarify that for everybody. So there's an asymmetry in the definition that I have over here. So my verification algorithm or verifier is not responsible for taking all of those paths of execution and making sure that it is indeed a no answer. It is given both W and C, right? Its job is not to tell you that W is a no instance. Its job is, okay, given C, I want to be able to check C to see if it's a yes instance. If it is not a yes instance, your job is just to reject. So if I make a guess is going to correspond to a path in this computation tree. Does everybody get the general gist of this? I just want to make sure you have some idea in the back of your head to convince yourself that this verifier idea actually has a natural relationship with the non-deterministic Turing machine. So is everybody okay with this? Just give me 2 thumbs up if we're okay with the idea here. And I want to address the question that was brought up about the certificate's length. So I want to revisit the question again of if P is a subset of NP. So from a verifier standpoint, so if you take this verifier-based approach to this, if I tell you a problem is in P, or language is in P, what would the certificate look like? Do I even need to look at the certificate? So if you go back to my definition of a verifier, in particular polynomial time verifier, do I really need to care about what the certificate even looks like? Well, the answer, of course, is still yes, because it was yes earlier, right? And I told you there's this natural correspondence. The way the proof goes, it essentially boils down to this. It essentially boils down to, yes, ignore C and just use W directly to solve the problem. Is C interpreted as is the path of acceptance? That would be the idea, yes. Yeah, so when I make these branching moves, these are going to correspond to me making some, I'm going to be checking over the certificate. But yes, yeah, so that's the idea. So that you make some guess, that guess is going to correspond to some path in this computation tree. And the whole idea is that if it's a yes answer, there most certainly is going to be one of these paths, right? And that'll tell you, yes, it is indeed a yes instance. But remember, my verifier's job is not to check all of the execution paths if the answer is no. It's just supposed to look at one path and say, no, just reject. But yeah, to answer your question about the proof, you can essentially just treat the proof like it was nothing. You can have it as an empty string. You can do that with the problems in P. So you just don't even need to care about what the proof is. You can just say, hey, look, just ignore the proof part. I'm just going to go after this with W. And because there exists a polynomial time algorithm that decides any language that's in P, I could just simply just say, hey, look, I could just look at W and just say, okay, my verification algorithm, A, it'll just tell me yes, accept. It just has to, you just run the algorithm you would use for when you determine that it is in P, right? So is everybody okay with this so far? So there's this verification way of thinking about this, and then there's just the pure non-deterministic Turing machine way of looking at it. So in some courses, like in complexity courses, they really like using this verifier-based approach. If you're one of these hardcore automata folks, they might really like to use this more non-deterministic Turing machine-based approach. Each is useful in its own right, so I shouldn't downplay either of these. So are we okay with this? Does this make sense to everybody? Okay, so if we're okay with this, I'm going to proceed with some examples. Actually, I have a question for you. Just actually an interesting question for you. There's actually other ways you can also characterize NP, by the way. So there's other equivalent definitions for NP. A lot of these are very interesting. One that's not as interesting as some of these others I may talk about, depending on how much time I have. Another one is, for example, I required that in my definition that it's always defined in terms of deciders, right? Believe it or not, you can actually get away with defining NP with respect to just being recognition. The reason why is because of this asymmetry I have with my verification algorithms. Does everybody see that? So notice that all I care about is the yes answers. If there's a yes answer, its job is just to say yes. There's actually a way you can reformulate NP in terms of recognizing as opposed to just saying it's always a decider. But there's an equivalency there, but that's something more of just an interesting exercise. I think in Hopcroft, in HMU, they have more details about it. But let me do some examples now. So let's try applying this idea of a verification algorithm. So I'm going to first consider a problem I'm going to call TSP decision. So this, in fact, is going to be what we're going to call the decision version of the traveling salesman problem. So here's the idea. So I'm going to be given a simple weighted complete graph. I'll give you a picture in the moment. Complete graph. G is equal to VE. So it has a pair. These are the vertices. These are the edges. Is there what we call a TSP tour? I'll show you what that means in a moment. A TSP tour of length or cost at most k. So this is a decision problem. The way you can tell right away is it asks you, it's usually, a lot of people like to formulate decision problems as a form of a question. That's a yes or no answer. So this is the traveling salesman problem, the decision version of it. This is not to be confused with the optimization version of this problem. So I'm going to draw you a fun picture just to give you an idea of what I mean by this. So suppose I have 5 vertices, and these can represent cities. My favorite places to go. I think I got 4, 4, 4, 4, 4. I'm not trying to summon the occult here. It's just a really fun looking design. Okay. So I'm going to assign numbers to all of the edges here. So first, is there anybody that's never seen what a graph is before? Just want to make sure. So I'm not just reiterating a lot of terminology. Because I will tell you what the traveling salesman problem is. I want to make sure that everybody's sort of familiar with the graph terminology. I know those that have been through 310 are all quite cozy with this. But just in case. I'm not seeing any issues, so I'll proceed. So I'm going to label all of the edges on the outer perimeter as 1. Then I'll have maybe 2, 4. Yes, yes. Okay. So when I'm drawing this, I'm talking about a mathematical object called a graph. This is not to be confused with a chart. What it is just a combinatorial object that has a list of objects called vertices. So these dots here, these circles, those are your vertices. The edges here, these are the lines that are connecting these vertices. You can think of these like ways I can go from one vertex to another. They connect them. We so-called say that they're adjacent if there's an edge between 2 vertices. So you might ask, okay, well, what does this mean? Another way you could think about it is just think about these circles here as cities, and the edges, these lines here that connect them, as roads to go between the cities. And what these numbers are going to represent, they can represent almost anything. There's an old saying that one CS prof that used to be in the department that I was an undergrad in, he always had this phrase that if you have a problem, there's most likely a chance it can be modeled as a graph. So here you could think about this as cities, and say the links or edges are in fact the roads that I can go from between the cities. I think I have 1, 1, 1. The numbers themselves don't matter a whole lot for us here. But the whole idea here is that I'm going to have all these with some distances. You can think of them as distances if you like. And if I were to tell you, okay, I want to know if there's a TSP tour. So a TSP tour is quite simple. It is just going to be what we call a simple cycle. So it's a simple cycle. Simple meaning that all the vertices in the cycle, except for the start and end, are unique. And it contains all vertices of G. So it's a cycle that consists of all the vertices of the graph, all these circles here. So all the cities. So your job is to give me a way I can go through a pathway around from city to city, where you don't repeat a city, but you have to visit all of them. Now, I formulated this as a complete graph to ensure that there's always going to exist some path, some TSP tour. It's just that we want a TSP tour typically where this total, like the sum of all of these edges. So its cost is the sum over all the edges in the cycle. So if I go over all of the edges in the cycle, so for example, there's this one along the outer perimeter. Notice that this is a TSP tour of total cost or total length of 1 plus 1 plus 1 plus 1 plus 1. And I get back to where I started. So I have 1, 2, 3, 4, 5. I have a TSP tour of cost 5. So what K is going to be here, is going to be this, it's going to be a bound on the total cost. So you can ask questions, for example, okay, is there a TSP tour whose cost is at most, say, 5? And I would tell you in this case that the answer is yes. It's right here, right? It's all along that outer perimeter. However, if I asked if it was, say, if I make K in this, if I made it, say, 3, for example, is this a yes instance or a no instance? Well, remember, gotta just substitute what K is right here. So given a simple weighted connected graph, complete graph. So imagine I give you this one. Is there a TSP tour of total cost at most K? And K is 3? If K is 3, then the answer is no, believe it or not. I can't find such a thing. So when I'm doing this, what I'm going to be interested in is if there's a TSP tour such that the answer is going to be yes, my verification algorithm's job is to tell me that indeed the answer is yes. Otherwise, it has to reject. Now, that brings me to talking about the certificate. So what the certificate should look like. And keep in mind, I get to pick what the certificate looks like, as long as its length is polynomial in the input length, okay? So here's a very simple suggestion. So a certificate that I would think might be a good idea. So if I pick as a certificate, if I use a tour or cycle, keep in mind, I'm not necessarily going to require it's a TSP tour. I'm just going to say it's some cycle in the graph. Would you agree with me that the length of this proof that you would encode with C, would this be polynomial in the length of the graph's description? Almost certainly it will be, because that graph also, it consists of vertices, right? All of them are encoded in W. So we're okay. So a very simple way of thinking about the certificate is as an answer, a potential answer, and your job is to check the certificate. Okay? So I'm going to do now a proof with you to show you that this problem is in fact an NP. So first, does everybody understand what TSP decision is? So you may know about the optimization version of this where you minimize K. Yes? Sure, no problem. Yeah, so the question is about how do you this K part, like this whole part here. So if I give you some graph, so the input for this problem is a graph and K. So your question is now dependent on what the graph looks like and what K is. So you have to answer yes or no. If it's yes, then that's input string, which would encode the graph and K, would be in this language. If the answer is no, it's not in this language. So if I give you answer yes, what that would mean is that there has to exist one of these TSP tours. That means it's going to have to visit all of the vertices without repeating a single one of these cities or vertices once. So you could think of this like if I was some delivery person and I want to go all the way through all of these locations I need to travel to without repeating my trip twice to a location. This has numerous applications in operations research. This is one of like the core problems of combinatorial optimization that people get very obsessed about. There's people who have spent their whole careers just studying just even special cases of this problem. It has numerous applications. You may as well call it like something like UPS. What's job of UPS? It's basically something like this mixed with some other scheduling problem. But yeah, so when I ask about K, this is a part of this input here. So if I give you a K value and the answer is yes, that means there has to be one of these tours such that if I add up all of those edge weights on the tour, it has to be no larger than K. If it is, so it means that I have to check. Now remember, checking the answer for this is very easy, right? I just give you a cycle and you just tell me if it's a TSP tour. And you check if its length is at most K. And that's in fact what our proof's going to look like. But the answer, if you want to tell me that no, there is no such TSP tour in this thing, would you see that that's actually a lot harder to do? Like if I just told you, yeah. Your job is just to like tell me, yeah, there is no TSP tour with total cost of most K, right? That's actually a much harder problem. In fact, the best known algorithms we have for doing that all take exponential time. That's why you'll notice that I'm using the certificate to help me determine if W belongs to the language or not. It's helping me verify it. Does everybody see that? So I'm going to show you. So first, does that clarify the concern about what exactly K's role is here? Excellent. No, sounds good. So let's proceed. Now let me try proving this for you. Then we'll do another example. So I must mention, like I said, the traveling salesman problem is one of these really infamous optimization problems. Even its decision version is very infamous too. In fact, you can use the same principle I described last day. Remember I talked about how there's a connection between optimization problems and decision problems? If you use that exact same game I described, where you can use binary search, like on K, for example, I had over here, you can see how you could potentially determine what the optimal value for a TSP tour is, right? So you see that there's a very close connection between them. You can tell me, for example, that TSP, the optimization problem, is going to be, like if I had at my decision problem, the optimization problem is at least as hard as the decision one, right? Because the optimization one has to tell me what the smallest K is, but it also has to actually give me what the tour looks like. Here, I just need to know if there is one or not. And usually that means I'm going to have to compute it out. Okay. So let's try proving this. So theorem, TSP decision is in NP. So here's the proof. So I'm going to describe to you now a polynomial time verifier. So I'm going to say we present a polytime verifier. So remember, you get to pick what the certificate looks like, but the natural one you should pick is something that's a potential. You got to think about this very much like if somebody gave you some algorithm that is actually supposed to compute the answer to you. And that's a really good intuition when it comes to picking the certificate. So for example, last I talked a little bit about the decision version of the minimum spanning tree problem. So I called it like, so the cost, I was trying to find a K, sorry, I was trying to find a spanning tree whose total cost was at most K. In that problem, a natural certificate to use there would just be a tree. So if I just give you some proof that's going to encode some tree, you can always just check. You just check if the tree is in fact a spanning tree whose total cost is the most K. You can do the exact same thing right here. So remember, that's the big part of this, is that the intuition that you want to use is that that proof is going to be something that somebody presents to you, and your job is just to check it, okay? But your verifier has to be capable of being able to tell you, yes, what I've just been presented is in fact what I'm looking for, in this case, a TSP tour of cost at most K, or it should be able to tell me, no, that what you just gave me doesn't. It isn't. Now, remember, that's not to be confused with the instance itself. So it's supposed to work properly if I give you a yes answer. Okay. So use a tour, a cycle, as a certificate. So I'm just going to describe to you my verification algorithm as almost like a little tester. The algorithm tests so first it checks if, let's give it a name, certificate C, because I gave it the name C before. If C contains each vertex exactly once. So remember, a vertex, that's one of our cities. Exactly once. And B, if the sum of the edges, the sum of the edge weights, let me be a bit more careful here. Sum of the edge weights, those are the numbers on the edges of edges in C does not exceed K. So we're going to test these two. You'd agree with me that if I give you some cycle, if it contains every vertex exactly once, you know, this is in fact going to be a TSP tour. And this is going to ensure that the total length of that, or length of the TSP tour, does not exceed K, which that's the other part of this. So all we do is if the above true, if both the above are true, then you can just simply return yes, which is accept. Otherwise, reject. And that's it. Can I convince everybody that that is in fact a polynomial time verifier? Does everybody see how this algorithm I just described to you takes polynomial time? So you can see that I just simply check if each vertex is contained exactly once. Now, in a model like the RAM model, I could just simply check this by just checking all the vertices and see if every single one of them appears in C, but it does it exactly once. And of course, all I do is I look at all of the edges that are going to be a part of this cycle, and I just simply sum over them. And I could do all of this, believe it or not, in actually quadratic time in the RAM model. So if both of these are true, do you see how this works just fine? So I just give you some certificate. Your job is just to check it, okay? So if it's a yes instance, this will most certainly tell you yes for W, where W is the input. So is everybody okay with this proof? So remember, the certificate, yes. Okay, yeah, so like I said earlier, the certificate, you want to think about this like, you remember, all of these are decision problems, but they answer yes or no, or they're in the language or not in the language, depending on which equivalency you'd like to use. But usually these problems involve some object that would be, in fact, need to exist for it to be a yes answer. So very often, the way you pick the certificate, remember, you want to make sure it's not too long. It has to be polynomial in length of the input. In this case, picking a list of vertices is most certainly okay because the graph itself is encoded with vertices and edges. So what you'd want to think about the certificate like is like, okay, so if I give you a potential answer, And the potential answer is going to represent the object at hand that would give me the yes answer. That's a good choice for a certificate. We're going to see another example. Is that okay? Just think about it like if I gave you something like when I talked about the minimum spanning tree problem, for example, when I had its decision version, a good certificate would just simply be just a tree. And then you could just say, okay, let me check if it's a spanning tree and its total cost is the most k. So that's sort of the asymmetry that exists with this definition, is that I get to decide that this exists. But it has to be of a certain length. But yeah, if you have any questions out, I'm going to do one more example because we have enough time for, I think, one more example here. So I'm going to present another problem, and this is another graph theoretic problem. It's called clique. So given an undirected graph G is equal to VE. So I have a set of vertices and edges, just like I did over here. Except now I'm not going to make any assumptions about all the edges being connected to one another. Sorry, all the vertices having adjacency with each other. I'm just going to assume it's some undirected graph with n vertices and edges E. And I'm going to assume there's some positive integer. So this is going to be the positive integer that's going to be a part of my yes or no decision. A positive integer k less than or equal to n. Is there a k clique? Is there a k clique? Now, if you don't know what that is, that's okay. Here's the definition of a k clique. It's a subset C of the vertices of size k, and for each pair. Now, I'm going to assume when I say each pair, I'm assuming that they're distinct. When I say that unique pairs that I'm going to be picking out, for each pair of vertices, UV in the set C, I can guarantee you that there's an edge that's going to be in G. So let me draw you a fun picture to illustrate this idea. Now, clique itself has numerous applications and things including such as social networks. And very often they're used for checking all sorts of things involving networks sometimes. Clique is not an easy problem. I must stress that. Again, this is another problem where the best known exact algorithms that solve it take exponential time. So let me draw you a fun picture. So I'm going to quickly draw you a picture. Then I'm going to do the proof showing you that cliques in NP, and then we'll stop for today on a question. So I'll try my best to finish this up prompto, okay, everybody? Okay, suppose I give you a graph that looks like this. And suppose, so this is my graph, and suppose I told you k is 4. So the question would be, is there a 4 clique, which would be a subset of the vertices, so those circles, such that when I look at any two pairs of the vertices that are going to be in this supposed k clique, there's going to be an edge in this graph for such in G. Does anybody see the clique? Is there a clique, a 4 clique in this? Yes, there is. It's right here, right? No! Let's just go with this one. Okay, here we go. It's right there, right? So in this case, the answer would be yes. However, if I give you something that looks like this, if, say, for example, I make k is equal to 4 here, is there a 4 clique here? Nah, right, exactly. So this one definitely does not have one. Checking for this is not easy. Sorry, I should say, when you're given one of these, it's not very easy to compute whether there is one or not. So, let me just do the quick proof here. Believe it or not, this is nice and simple. So, proving NP, I guess a problem is in NP. The difficulty of doing so can vary. A lot of the standard problems you may be familiar with or may have encountered before, they very often have very nice and simple proofs to them. It's kind of funny that way because this is all about checking easy proofs, right? Just to check if it's easy to check the answers. But there's sometimes there actually are cases where showing something, a problem is in NP is not straightforward. There's sometimes problems that are sitting out there. I can think vaguely off the top of my head of a problem like in computational geometry. I think it was involving string graphs. It took a number of years for them to figure out it was an NP or not. But anyways, let me describe this to you. My point is that typically you'll see that they'll have a format very similar to this. But sometimes I shouldn't try to give you the false impression that they're always easy to do. So first, let us describe a polytime verifier. So we're going to use a clique. So remember, this is just a subset of vertices. If you prefer to say subset of vertices, that's okay. Either one is perfectly fine because I'm going to presume that the answer is yes when I'm doing this. My job is just to make sure it actually is indeed the case. So as the certificate. Okay, certificate C, then here's what the verifier is going to do. Test whether C is a subgraph with k vertices in G. First step. So you just simply look at the subset of vertices. So you just check to make sure each one of those is a vertex in the graph. And you indeed check to just make sure that all of these edges are in fact existing in the graph itself. So you just do some simple comparison just to make sure that this thing is indeed a subgraph. Meaning that it consists, if I take those vertices and I look at the clique, okay, so I need to know that those edges in fact exist. But this rolls me into the second part. The second part's really where you're going to do that check for the edges. Then determine whether G contains all edges connecting isn't the greatest of technical terms. Connecting vertices in C. And of course, same idea. If both tests pass above, you just return yes, aka you accept, otherwise reject. So if you looked at this proof, you should be convinced that this all can be accomplished in polynomial time. If I give you some subset of the vertices, you can indeed check that this subset of vertices is going to comprise a subgraph with k vertices in G. And then you could simply just check if you could check all those pairs, like the definition I have over there. And then you just see, okay, if they're both satisfied, then you just say, yeah, this most certainly has to be the case. So it's just like, remember, back to before, just think about it like I'm just taking a guess, where I look at the certificate like it's a guess. If I know the answer is yes, I need some way of checking that. That's the point of the verifier. So I have a natural question for you, and I'll leave it on this because I apologize for going a little longer. Is NP a subset of P? So I'll let you think about that. We'll talk more about what that might even mean next time, okay? Yes, this is a very important question. Theoreticians and computer scientists, mathematicians have been interested in this question for decades now, by the way. So I'll let you think about what this would mean, and we'll talk more about it next time, okay, everybody? So when I come back, we'll talk more about that. So I'll see everybody later, okay?